This question is about finding maxima and minima in a multivariate setting. So it's just like calculus 1, where you take the derivative, set it equal to 0, and solve. Except now we have partial derivatives instead of derivatives, but we're just going to take the partial derivatives and set those equal to 0 and then solve the resulting system of equations. So let's do that. So here we do the partial derivative of this function with respect to x is e to the x cosine y. Okay, so setting that equal to 0 gives us one equation. And the partial derivative of this function with respect to y gives us minus e to the x sine y equals 0. So now we have two equations. We have to solve the system of equations. So you probably know, just because it comes up a lot in calculus 1, that there's no x that you can put into e to the x that makes it equal to 0. Graph it and convince yourself that that's true. So e to the x isn't doing anything as far as whether or not this is true. So we can write down sort of an equivalent system of equations. We're looking for a y that makes cosine y equal to 0 and at the same time makes sine y equal to 0, or negative sine y, same thing. And there just is no y that does this. Okay, so this system of equations has no solution. So that means that this function has no critical points. And critical points are the only candidates for local maxima and minima, so this function has no local maxima and no local minima and no saddle points. So none. And if you look at a graph of this, you can convince yourself that it's true. This thing makes actually a pretty cool graph. So here's the graph of e to the x times cosine y. So, you know, this is going in sort of the x direction. It's going up, just like the exponential function. And then as you go in this direction, cosine y is making things positive and negative. So you get this pretty sort of folded shape. But the important thing to notice is that there are no local maxima, no local minima, and no saddle points. So the picture agrees with our derivation. Now let's do another problem of the same type. So again, we want to find the local minima, the local maxima, and the saddle points, if any. So it's the same strategy. Take the partial derivative with respect to x. That gives 3x squared y plus 24x as the partial derivative with respect to x. And we're going to be setting this equal to 0 as one of our equations. The other equation is going to come from the partial derivative with respect to y. And that is x cubed. This just goes to 0, and this becomes minus 8 equals 0. Okay. And we got lucky as far as the system of equation goes, because the second one here is just obviously x equals 2. So that's the only way that could be true. Alright, and if x equals 2, what happens to the first equation? This becomes 3 times 4 y plus 2 times 24 is equal to 0, and that means y is equal to minus 48 divided by 12, and so that is minus 4. So we have exactly one critical point for this function, and that's the point 2 comma negative 4. And now the question is this a local max, local min, or a saddle point? So how do we do that? We use d. And so you might remember that d is fxx times fyy minus f of xy squared. And there are some rules for, you know, this thing takes a point as input. If you forget this formula, you can recover it if you can remember this matrix, because it's just the discriminant of this matrix. Fxy, no, is that right? Yeah, I think so. Now fyx, fyy. So d is also the discriminant of this matrix. If you forget the formula, then using Clairaut's theorem for the equivalence of these two things, you can recover it. And great, so let's plug the given point into D and see what happens. All right, but in order to do that, we have to know what the second partials are. So let me copy these so that I can refer to them down here where I can do some more work. Okay, so I need to know what the second derivative with respect to x is, for one thing. So what is that going to be? fxx. That's going to be 6xy plus 24. Okay, and all right, and I also need to know fyy, and what is that going to be? That is just going to be 0. Oh wow, okay, so that means that this first part is just going to be 0. So this is going to be 0 minus, and now I need to do fxy. So the partial with respect to x followed by taking the partial with respect to y gives you 3x squared. And then if you plug the point 2 minus 4 in for x and y here, there's really just an x. Then you get 3 times 4 is 12. So this is minus 12. Okay. And now the rule is that since d is negative, it follows that the point 2 minus 4 is a saddle point. And that means neither a local max nor a local min. And let me show you the picture. This is the picture, and you can see that it is indeed a saddle point. You could straddle that thing if you wanted to. So, you know, the point that we found is somewhere in here. And that's pretty much it. I guess we could, just for the heck of it, go over some other possibilities. So some other possibilities are, what if D is positive and fxx is negative? Let's say that this had happened at this point, even though it didn't. Then, you know, just like in calculus 1, this would, if the second derivative were negative, that would mean concave down, and concave down means that a critical point is a max. Then AB is a max. Or I guess if you're being precise, you should say that local maximum occurs at AB. And so the other possibility is if the derivative is positive and fxx is greater than 0, then what would happen in calculus 1? You would say the second derivative is positive, so that means concave up. And then if you have a critical point, it's going to be a min. So in this situation, local min occurs at A, comma B. So, you know, we finished the problem at this stage, but I just went on to remind you what the other possibilities are. And that's it. Pretty easy type of question.